The 12.7 by 108 mm round punches through 0.8 of an inch steel armor from over half a mile away. Muzzle velocity, 2,800 feet per second. Muzzle energy, 13,000 foot-pounds. That's 30 times more than a standard rifle round. One cartridge weighs 4.5 ounces. Length, nearly 6 inches. But how do you manufacture this in a country under sanctions, cut off from Western technology? Today you'll see the complete production cycle of large-caliber ammunition in Iranian factories, from copper sheet to a round that flies faster than sound. If you want to see how a defense industry operates under isolation, hit subscribe. Here we show you manufacturing facilities nobody talks about. Iran's been making ammunition since the 1940s. After the 1979 revolution and the war with Iraq, the country got hit with sanctions. Western suppliers pulled out. They had to build everything themselves. The Defense Industries Organization, DIO, runs 20 factories. The AMIG Ammunition Production Group cranks out calibers from 5.56 mm all the way up to 152 mm. The 12.7 by 108 mm caliber? That's Soviet standard. Think of it as the Russian equivalent of the 50 BMG. It's used in heavy machine guns like the DSHK and NSV, in anti-materiel rifles, in anti-aircraft guns. The factory sits in the mountains about 30 miles from Tehran. 50 acres, 1,200 workers. Production runs 24/7, 3 8-hour shifts. They pump out 150,000 rounds a day. That's 55 million a year. The casing is made from brass. Brass is an alloy of copper and zinc. Copper content, 70%. Grade, L70. Brass is ductile. Stamps well, doesn't rust. Supplied in sheets 0.08 inches thick. Sheet size, 3.3 feet by 6.6 feet. Weight, 75 pounds. The sheet is cut into circular blanks 2.75 inches in diameter. A 200-ton press. Guillotine blade. One sheet yields 400 blanks. The blank is stamped on a drawing press. The punch drives into the center. The metal stretches into a cup. Cup diameter, 1.1 inches. Height, 1.18 inches. Wall thickness, 0.06 inches. Force, 50 tons. The cup goes through 7 drawing stages. After the 7th, diameter 0.62 inches, height 4.25 inches, wall thickness 0.04 inches. The base is thicker, 0.12 inches. In the center, they drill a primer pocket 0.25 inches in diameter. Depth, 0.24 inches. On the outside near the base, an extractor groove. Width, 0.12 inches. Depth, 0.03 inches. After stamping, the brass is work-hardened. Tough and brittle, it needs annealing. The cases get loaded into a conveyor-type furnace. Temperature, 1,000 to 22 degrees Fahrenheit. 20 minutes, the brass softens. Stresses release. Air-cooled. Then they're sized through a ring with an internal diameter of 0.62 inches. Tolerance plus or minus 0.0008. The neck gets crimped into a 4-degree taper for a tight bullet fit. Cases are washed in alkaline solution. 3% concentration. Temperature, 140 degrees. 5 minutes. Strips off the oil. Dried with hot air at 212 degrees for 3 minutes. The bullet's made from lead and steel. Steel core. Grade 70 steel. Hardness, 220 Brinell. A rod, 0.35 inches in diameter, gets cut into blanks 1.38 inches long. Machined on an automatic lathe. Shape, cylinder with a tapered nose. Length 1.3 inches. Diameter 0.346 inches. Weight 0.67 ounces. The casing is made from tombac. Tombac is brass with high copper content. 90% copper, 10% zinc. Harder than regular brass. Tombac comes in strips 0.035 inches thick. Stamped on a press. Creates a cup half an inch in diameter, 0.8 inches tall. Drawn in 3 stages. Final specs. Diameter half an inch, length 2.5 inches, wall thickness 0.028 inches. A steel core goes inside. The space gets filled with lead. Lead melts at 630 degrees Fahrenheit. The casing with the core goes into a mold. Pour. Lead solidifies in 3 seconds. Automated. Output 2,000 bullets per hour. Finished bullet. Length 2.5 inches, diameter half an inch, weight 1.7 ounces. Shape: pointed nose with boat tail. Ballistic coefficient 0.55. Range: up to 2 miles. They use SNP powder, spherical nitroglycerin type. Base: nitrocellulose and nitroglycerin. 50-50 ratio. Stabilizers: diphenylamine, 2%. Plasticizers: dioctyl phthalate, 3%. Powder comes as spheres, diameter 0.047 inches. Density: 100 pounds per cubic foot. Heat of combustion: 4,000 joules per gram. Burn rate: 0.79 inches per second at 43,500 psi. The charge is dispensed automatically. Weight: 0.46 ounces. Accuracy: plus or minus 0.02 ounces. Poured into the case through a funnel. Primer pressed into the primer pocket. Brass cap, diameter 0.25 inches, height 0.2 inches. Inside, percussion compound. Mercury fulminate 30%, potassium chlorate 40, antimony sulfide 20, ground glass 10. Compound weight 0.003 ounces. Pressed with 330 pounds of force. Seating depth 0.004 inches below the case head. If the primer sticks out, it could detonate during feeding. The bullet gets inserted into the case mouth. Fit is tight. Force: 110 pounds. Depth: half an inch. The neck gets crimped using a roller. 3 ring grooves hold the bullet in place. Red shellac-based lacquer gets applied to the neck. Seals the joint, protects the powder from moisture. The primer gets sealed too. A drop of lacquer around the edge. Rounds complete. Length: 5.8 inches. Bullet diameter: 0.50. Case diameter: 0.62. Weight: 4.4 ounces. Bullet weight: 1.7 ounces. Powder weight: 0.46 ounces. Muzzle velocity: 2,800 feet per second. Muzzle energy: 12,700 foot-pounds. Maximum chamber pressure: 52,000 psi. That's 3,600 atmospheres. Every batch gets checked. Each batch is 10,000 rounds. They pull 10 at random. Fire them from a test barrel in a concrete bunker. Walls 3 feet thick. They measure bullet velocity with an optical chronograph. 2 frames spaced 3 feet apart. Bullet crosses the first. Timer starts. Crosses the second. Stops. Computer calculates velocity. Standards 2,700 to 2,800 feet per second. Spread no more than 30 feet per second. They check grouping. 10 rounds at a target from 300 feet. Maximum spread 6 inches. Average deviation 2. They check penetration. Targets a steel plate 3/4 of an inch thick. Range 1,000 feet. Bullet has to punch straight through. If even one of the 10 fails, the whole batch gets rejected. 10,000 rounds go to reprocessing. Casings get melted down. bullets too. Powder gets burned. Cartridges that pass inspection get packaged. 100 rounds in a wooden crate, 20 by 12 by 8 inches. Weight, 33 pounds. 5 rows of 20. Cardboard dividers between rows. The crate gets nailed shut. Marked with paint. Caliber, quantity, date, batch number. Shipped to warehouses. Underground bunkers in the mountains. Depth, 160 feet. Temperature held constant at 59 degrees. Humidity at 60%. Storage life, 10 years. Then testing. Passed the test. Extended another 5. The 12.7 by 108 mm round is used in the DSHK heavy machine gun. Rate of fire, 600 rounds per minute. Effective range, nearly a mile. Maximum range, almost 2 miles. Penetrates body armor at over half a mile. Punches through a 12-inch brick wall. Stops unarmored vehicles. Destroys radar and optics on armored vehicles. Iran produces these by the millions. Exports them to allies. Without access to Western technology, the country built a complete production cycle, from copper to combat round. This is how ammunition gets made under sanctions. If you found this interesting, hit that like button. Comment below if you knew about Iran's defense industry. Subscribe. We show you what others won't talk about. Every rock you hold in your hands could be hiding miles of wire. Sounds insane, but it's true. Copper ore, this gray-green boulder, holds millions of tons of metal that powers every city on the planet. Every wire in your home, every cable underground, every power line stretching across continents. It all started with a chunk of dull rock that got blasted, crushed, and melted at 2200 degrees. Humanity extracts 25 million tons of copper every year. That's the weight of 4,000 Eiffel Towers. Each ton requires blasting 100 tons of rock, drilling hundreds of feet deep into the earth, processing mountains of stone, and all for a metal that makes up less than 1% of the ore's mass. How do you extract red metal from gray rock? Metal that conducts electricity better than anything else on Earth. How do pits nearly a mile deep give birth to wires that light up megacities? Stick around till the end. You'll see how rock becomes the energy of civilization. Chuquicamata, northern Chile. The Atacama Desert, the driest place on Earth. Home to the planet's largest open-pit copper mine. Depth, 3,300 feet. Width, 2.5 miles. Length, 3 miles. A wound in the Earth's crust, visible from space. Excavators the size of a 3-story building gnaw at rock around the clock. Each bucket, 700 cubic feet. In 1 hour, a single excavator tears out 1,000 tons of ore. Bel AZ dump trucks with wheels 13 feet high haul 300 tons per trip. The road out of the pit, a serpentine stretch 12 miles long. Trucks spiral upward for an hour just to reach the surface. Chile produces 6 million tons of copper a year. That's 28% of the global market. Peru delivers 2.5 million tons. China mines 1.5 million but consumes 14 million. The rest it buys. The US produces 1,200,000 tons. Russia, 700,000. Copper is a strategic resource. Without it, no power grids, no communications, no electronics. Countries fight over deposits more quietly than they do over oil, but no less fiercely. Mining starts with explosions. 100-foot-tall drill rigs bore 12-inch diameter holes 65 feet deep. The well pattern is calculated to the inch. Distance between holes, 16 feet. Each one gets packed with ammonium nitrate mixed with diesel fuel. ANFO, the cheapest explosive there is. One charge, 650 pounds. A single bench takes 400 tons of explosives. Detonation controlled by electronic timers. Each hole blows with a 10 millisecond delay. That creates a destruction wave that fractures the rock without throwing it far. The blast lasts 3 seconds. Sound like an earthquake carries 20 miles. The ground heaves. A 1,000-foot column of dust rises from the pit. When the dust settles, you're looking at 2 million tons of fractured rock. Excavators move in. 24 hours to haul it all out before the next blast. The conveyor never stops. Blast, haul, drill new holes. Blast again. The pit grows 65 feet deeper every year. "6,000 years ago, on the island of Cyprus, people found a strange stone. Green, heavy, with a metallic sheen on the break. When they threw it into the fire, the stone melted and a red liquid flowed out. As it cooled, it turned into metal, soft, flexible, shiny. The ancients called it cuprum, after the island of Cyprus. They made knives, axes, jewelry from copper. But the major discovery happened in 1831. Michael Faraday created the first electric generator. Turns out copper conducts electricity better than any affordable metal. 6 times better than iron. 1.5 times better than aluminum. Only silver beats it, but that's way too expensive. Copper became the perfect conductor. In 1879, Thomas Edison built the first power station on Pearl Street in New York. Copper wires stretched through the streets. Cities began to glow at night. The era of electrification had begun. Demand for copper exploded. What was once used for coins and statues became the backbone of energy. Quarries expanded. Mines went miles deep. Humanity started devouring copper by the ton. The 20th century transformed copper into civilization's circulatory system. Every house requires 440 pounds of copper. Wiring, pipes, radiators. One car, 50 pounds of copper in the alternator, starter, wiring. One wind turbine, 9,000 pounds of copper in the generator windings. A Tesla factory for battery production, 22 million pounds of copper annually. A power transmission line across Siberia, 660 million pounds of copper and thousands of miles of wire. By the start of the 21st century, humanity was mining 33 billion pounds a year. By 2020, 55 billion, a 60% increase in 20 years. The reason: electrification of developing countries. India's building new cities. China's laying high-speed rail. Africa's installing solar panels. Copper's needed everywhere. The problem is, rich ores are running out. Ore used to contain 5% copper. Now, 0.5%. To extract 1 ton of metal, you need to process 200 tons of rock. Pits are getting deeper, processes more complex, cost higher, but demand's growing faster. Ore from the pit heads to the processing plant. This is where chemistry and physics kick in. First step, crushing. Jaw crushers grind refrigerator-sized rocks down to 4-inch chunks. Cone crushers pulverize them to gravel. Ball mills turn gravel into sand. The mill's diameter, 26 feet, length, 40. Inside, steel balls weighing 110 pounds each spin around. They pound the ore, grinding it to powder. After 8 hours of rotation, the ore becomes dust. This dust gets mixed with water, creating slurry. It flows through flotation machines. These are giant tanks with air pumped in from below. Air bubbles get coated with flotation reagents, chemicals that stick to copper particles. Copper floats to the surface in foam. Waste rock settles to the bottom. The process runs through 10 stages. Each stage increases copper concentration. At the input, 0.5%. At the output, 25%. That's concentrate. From 100 tons of ore, you get 2 tons of concentrate. The remaining 98 tons? Waste that gets stored in tailings ponds the size of a lake. The concentrate heads to a copper smelter. Here it's turned into pure metal. First stage, roasting. The concentrate is heated to 1300 degrees Fahrenheit in the presence of oxygen. Sulfur burns off as sulfur dioxide gas. What's left is sinter, a mix of copper and iron oxides. The sinter gets loaded into a reverberatory furnace. Temperature 2200 degrees. Silica flux is added. Iron bonds with the silica and floats up as slag. Copper settles at the bottom as matte, an alloy that's 50% copper. The matte is poured into a converter. Pure oxygen is blasted in under pressure. Remaining iron and sulfur burn away. Temperature climbs to 2370 from the exothermic reaction. After 6 hours of blowing, what's left in the converter is blister copper, 98% pure. But that's not enough for wires, you need electrolysis. Blister copper is cast into anodes 2 inches thick. They're submerged in tanks filled with copper sulfate solution. A current of 2 volts runs through. Copper dissolves off the anodes and deposits onto cathodes. After 3 weeks, the cathodes are coated with a layer of pure copper 4 inches thick. Purity, 99.99%. This is market-grade copper, ready to become wire. And just like that, after a journey from an explosion in a half-mile deep quarry through crushing, flotation, smelting at temperatures above 1800 degrees Fahrenheit, and electrolysis, gray rock transforms into red metal that carries electricity to every home on the planet. Without copper, there'd be no light in cities. No internet. Every data center runs on copper bus bars. No electric cars. A single Tesla contains 175 pounds of copper. No renewable energy. Solar and wind farms need 3 times more copper than coal plants. Every year, humanity lays down 6 million miles of copper wire. That's the distance from Earth to the Sun and back 7 times. 25 million tons of metal connecting continents into a single electrical grid. Copper is civilization's nervous system. Electrical impulses race through copper veins like thoughts through neurons. Factories operate, hospitals save lives, homes glow in the night. All thanks to metal that was once just green rock in the ground. Every time you flip a light switch, remember, between your finger and that bulb, miles of copper wire born from an explosion in a desert quarry on the other side of the world. It's the magic of turning stone into energy. And this magic won't stop as long as cities shine. There's something almost poetic about watching a massive steel plate, thick as your fist, transform into a perfect cylinder. What we're seeing here is one of Central Europe's finest engineering firms working with a steel plate 4 3/4 inches thick, nearly 10 feet wide, destined to become a cylinder with a 55-inch diameter. For those of us who remember when heavy industry was the backbone of manufacturing, this is the kind of craftsmanship that built the world we know. The star of this operation? The plate rolling machine. And let me tell you, this Italian marvel is about as perfect as metalworking equipment gets. The company's been perfecting this craft since 1946, right after World War II, when Europe needed reliable machinery to shape the infrastructure of the modern age. The machine operates on a 3-roller pyramid principle, which has been the gold standard for rolling heavy plates since the Industrial Revolution, though the precision we're seeing here would have blown the minds of craftsmen from that era. Here's how this beautiful process unfolds. A steel plate, which has been preheated to reduce brittleness, gets positioned between 3 massive cylindrical rollers arranged in a triangular configuration. The 2 bottom rollers are the driving force, rotating in synchronized harmony to pull the plate through, while the top roller, which can be hydraulically adjusted to within fractions of a millimeter, applies downward pressure, creating the curvature. Think of it like rolling out dough, except this dough weighs several tons and could support a building. The operator, working from a computerized control panel, inputs the desired diameter and thickness parameters. The machine's sophisticated sensors continuously monitor the bend radius, making real-time adjustments through hundreds of hydraulic cylinders. Remarkably, despite working with such massive forces, the machine achieves tolerances that would make a Swiss watchmaker proud. The plate makes multiple passes through the rollers, bending a little more each time, gradually approaching that perfect cylindrical form. This incremental approach prevents stress fractures and ensures uniform curvature along the entire length. As the plate begins its transformation, you can actually see physics at work. The outer surface of the bend stretches while the inner surface compresses, and the metal flows like frozen honey, maintaining its structural integrity while taking on this new shape. Now, let's step into the world of heavy forging, where tradition stretches back to the blacksmiths of ancient Rome. Except now we're working with hammers that make Thor's hammer look like a toy. What's especially mesmerizing is the combination of raw power and surgical precision. We're watching parts being forged that can weigh up to 250 tons. The process begins long before the hammer ever strikes. Steel ingots, fresh from the mill, are slowly heated in gas furnaces to temperatures around 2,200 degrees Fahrenheit. This isn't a rushed process. Depending on size, heating can take anywhere from 8 to 24 hours. Once the steel reaches that perfect forging temperature, glowing that unmistakable orange-yellow color that means it's ready to flow, the real dance begins. Massive manipulators, essentially industrial robotic arms that can rotate and position these multi-ton pieces with remarkable delicacy, move the workpiece under the forging press. Both hydraulic presses and mechanical hammers are used, depending on what the job demands. A hydraulic press applies slow, steady pressure, ideal for ensuring the force penetrates deep into the heart of the piece, eliminating any internal voids or inconsistencies. The mechanical hammer, on the other hand, delivers rapid blows that shape the surface and create specific forms. The forge master, a craftsman whose skills require decades to develop, orchestrates this symphony of heat and pressure. Between each strike or pressing, the piece rotates, gets repositioned, and sometimes reheated. This is called open die forging, because unlike closed die forging, where metal is compressed into a specific shape, here the masters are literally sculpting the metal through repeated strikes and pressure applications, gradually drawing it into the desired form. Each strike refines the grain structure, making the steel stronger and more reliable than anything achievable through casting or machining alone. Now let's move on to modern precision forging, which has adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisan forging. The process starts with steel bars, often supplied in coils, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion, but within seconds, a steel billet placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. The secret lies in electromagnetic induction, discovered by Michael Faraday way back in 1831, but only practically applied to industrial heating in the early 20th century. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2,000 and 2,300 degrees Fahrenheit. Depending on the steel grade, the billet moves to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. What's remarkable is the speed and precision of modern forging presses. We're talking about machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. There's something deeply satisfying about watching skilled craftsmen build storage tanks. The process begins with selecting and cutting steel plates. Modern fabrication shops use CNC cutting tables, plasma or laser, that can slice through thick steel plate with remarkable precision, following computerized patterns that ensure minimal waste. But before any cutting happens, there's meticulous layout work, figuring out how to arrange different components to get the most from each plate. It's a puzzle that combines geometry, efficiency, and material science. After cutting, the components move to rolling and forming operations. Tank shells typically need to be cylindrical, which means flat plates must be rolled into curves using 3-roll bending machines like the ones we saw earlier. The edges of these rolled sections are then prepped for welding, usually with beveled cuts that let the weld penetrate completely through the material's thickness. The welding process, that's where the craftsmanship really shines. Tank fabrication typically uses submerged arc welding for the main seams, a process where the arc works under a blanket of granular flux, protecting the weld from atmospheric contamination while allowing deep penetration and high deposition rates. End caps, whether they're flat, dished, or hemispherical, get fitted and welded on, and then comes the real test, hydrostatic testing. The completed tank gets filled with water and pressurized above its operating pressure to verify integrity. Any leaks or weaknesses show up here, not during service, which could be catastrophic. Let's wrap up with the 3-roll plate bending operation, because there's something fundamentally impressive about watching these machines transform flat steel into curves with such apparent ease. The 3-roll bending machine is one of those elegant engineering solutions that's remained fundamentally unchanged for over a century because, simply put, it works beautifully. The machine consists of 3 essential rollers arranged in a pyramidal or triangular configuration. The 2 bottom rollers are drive rollers that grip and feed the plate through the machine, while the top roller, which can be adjusted up or down hydraulically, provides the bending force. The beauty of this setup is in its simplicity and efficiency. By varying the top roller pressure and making multiple passes, you can achieve a wide range of diameters and even create nearly perfect circles. The process itself is mesmerizing to watch. The plate enters between the rollers, and as they rotate, you can literally see the flat material take on curvature. For thicker plates or tighter radii, multiple passes are necessary, with each pass increasing the curvature incrementally. Modern machines can handle impressive specs. Plates several inches thick and many feet wide, bending them into cylinders or cones with remarkable precision. The rollers themselves are precision-ground, hardened steel, designed to maintain their shape under enormous loads. This technology represents a perfect marriage of time-tested mechanical principles with modern control systems, creating tools that are simultaneously powerful and precise, capable of forming the steel that builds our world.